Welcome to the Foundry by Forge College. I'm absolutely thrilled to have you here for today's explainer on ASIC architecture and performance. Now, if you caught our previous lesson on the overview of mining hardware, you already know the massive role these specialized machines play in the Bitcoin network. But today we're going to peel back the cover and look right at the internal blueprints of an ASIC. We're going to demystify exactly how chip-level engineering choices impact your hashing throughput, your thermal limits, and your overall performance per watt. And the best part is, by the end of this, you'll be able to understand a manufacturer's spec sheet without needing a PhD in thermodynamics.
So here's a quick look at our agenda for today. Section 1 is the ASIC factory blueprint. Section 2, throughput, speed, and cores. Section 3, power, efficiency, and heat. Section 4 covers device alpha versus beta. And finally, Section 5, our key takeaways.
All right, let's jump right into Section 1, the ASIC factory blueprint, treating chips like assembly lines.
To really get this, I want you to completely discard the idea that a mining rig is just some magic black box that turns electricity into Bitcoin. It's not magic, guys. It's actually a highly specialized microscopic factory. ASIC stands for Application-Specific Integrated Circuit. Unlike the CPU in your laptop, which is kind of a jack-of-all-trades that can run a web browser or play a video game, an ASIC trades all of that flexibility for extreme specialization. Imagine tearing down a massive, flexible car manufacturing plant and replacing it with a factory designed exclusively to produce exactly one specific identical widget, like, say, a left-handed spatula, and it produces it billions of times a second. That level of extreme specialization is precisely why ASICs absolutely dominate Bitcoin mining today.
It's kind of amazing how perfectly the internals of the chip actually map to our factory metaphor. Step 1 is the widget itself. In our case, that's one completed SHA-256 double hash. Step 2 represents the workstations along the assembly line. Inside the chip, we call these pipeline stages, and each stage performs a very specific, deterministic micro-operation on the data before handing it off to the next guy. And step 3, that's the conveyor belt, which is the clock frequency of the chip. Every time that clock ticks, the conveyor belt moves forward exactly one station. If you've got a deeply pipelined factory, once it's all primed and running, a brand new finished widget pops right off the end of that belt with every single tick of the clock.
Moving on to Section 2, throughput, speed, and cores. How to pump out more widgets.
Now, if you own this microscopic factory, your absolute main objective is to maximize your output, right? In the mining world, output is called hashing throughput. It's the total number of completed hash operations a machine can produce every single second, and it's typically measured in terahashes per second, or THSAS. You can think of this as the ultimate speed metric of our factory. But how do engineers actually increase that throughput? Well, let's take a look. Chip designers basically have three main levers they can pull to upgrade the factory, but every single one of them comes with a trade-off. First up, they can increase frequency. That essentially means speeding up the conveyor belt. It definitely yields more widgets per minute, but you're going to need stronger motors, which means pulling way more electricity. Second, they can add more cores. This is literally just building parallel assembly lines right next to each other. It massively boosts output, but obviously it takes up valuable physical space on the silicon. Third, they can shrink the process node. Back in our factory, this is like buying lighter, futuristic, ultra-efficient tools for the workers. It allows them to work faster while using less energy. But retooling an entire facility with brand new silicon technology, yeah, that costs an absolute fortune.
This brilliantly illustrates the impact of those architectural choices we just talked about. A single core? That gives you pretty low throughput. A deeply pipelined core, where the work is split into a bunch of hyper-efficient stations, gives you medium throughput. But if you're after maximum throughput, you have to replicate those cores. Parallelism is, for sure, the simplest and most effective lever for massive throughput. You just stamp out hundreds of identical assembly lines side by side. But as we're about to see, all those parallel lines crammed into one tiny space create a very specific physical problem.
Which brings us to Section 3, power, efficiency, and heat. The physical limits of the factory.
Before we talk about the heat issue, we absolutely have to introduce the golden formula of mining hardware. It's joules per terahash, or J/TH. This is the exact spot where brilliant engineering runs headfirst into the harsh physical limits of thermodynamics. You calculate this by taking the power in watts and dividing it by the hash rate in terahashes per second. This simple little number tells you exactly how much energy it costs to produce one single unit of hashing work. It is the ultimate measure of performance per watt. The lower this number is, the more efficient your factory is, period.
But let me ask you a question. What do you think happens when you run millions of these microscopic assembly lines at hyperspeed, pulling all that wattage inside a tiny little silicon chip? Well, just like a real factory running its heavy motors at maximum capacity without any ventilation, things get incredibly hot, incredibly fast.
Here are the raw thermal realities every miner has to face. First off, packing all that power into a tiny space creates intense hotspots. To avoid literally melting itself, the chip triggers what's called thermal throttling. It hits the brakes on the conveyor belt. Because of this, a machine's advertised peak throughput will quickly plummet down to a much lower, sustainable throughput. And finally, constantly baking your hardware degrades its lifespan over time. This is exactly why we always emphasize checking for steady-state, sustained performance numbers on those spec sheets, not just the flashy peak numbers some marketing department decided to put out.
And keeping those chips cool brings us to an incredibly important metric, PUE, or power usage effectiveness. You see, raw chip efficiency isn't the whole story. If your factory generates a ton of heat, you have to run a massive HVAC system to cool it down, right? PUE measures this facility overhead. If you have a highly inefficient machine, you aren't just paying for the electricity to run the chip itself. You are paying a massive premium for the giant fans and ambient cooling systems required to keep the thing from destroying itself. You always have to multiply your raw J/TH by your facility's PUE to get your actual real-world energy cost.
Okay, Section 4, Device Alpha versus Beta. Putting the specs to the test. Let's see this in action.
Let's introduce our two contenders. Over on the left, we've got Device Alpha. It's a modern design running at 110 terahashes per second, pulling 3,250 watts. On the right, we have Device Beta, an older model pulling 3,000 watts but only generating 60 terahashes per second. At first glance, a beginner might just look at the wattage and think, hey, they both draw around 3,000 watts, they must be somewhat comparable in operational cost. But look at the massive difference in output.
Let's run the math using our golden formula. For Device Alpha, 3,250 watts divided by 110 TH/S gives us a raw efficiency of 29.5 joules per terahash. Device Beta gives us 50 joules per terahash. That means Alpha is using roughly 40% less energy to do the exact same amount of work. Now, let's add a facility cooling overhead. Let's say a PUE of 1.15. Alpha's adjusted costs jumps to 34.0, but Beta climbs all the way up to 57.5. That PUE penalty hurts Beta significantly more because it's generating way less hash for the massive amount of heat it puts out. Now, let's look at the brutal reality of scaling this up to a real commercial level. Let's say you want to build a facility with 1,100 terahashes of capacity. You could buy 10 Device Alphas to get there, or you'd need 18 Device Betas. 10 Alphas will pull 32,500 watts. 18 Betas will pull a staggering 54,000 watts. Think about our factory metaphor for a second. You'd need almost double the physical real estate for the Betas. Vastly more shelving, thicker cables, and a much more expensive cooling system, all just to get the exact same output as 10 Alphas.
So what's the underlying diagnosis here? Well, Alpha is clearly using a newer process node. They went out and bought those better tools. Beta, on the other hand, suffers from a much higher power density per hash. It's working harder and sweating way more. Because Alpha is more efficient, it runs cooler and easily avoids that dreaded thermal throttling. Ultimately, choosing Beta doesn't just spike your monthly electricity bill, it drastically inflates your upfront capital expenditures for space and cooling. It's a lose-lose.
Finally, Section 5, Key Takeaways. The final engineering punch list. Let's wrap this up.
Here are your blueprint rules to take away from today. First, remember that throughput is always a delicate balance of replicating cores and pushing clock speed. Second, never trust a marketing brochure at face value. Always grab your calculator and figure out the JTH yourself, which is just power divided by hash rate. Third, raw chip efficiency is not enough. You absolutely must adjust for facility PUE to find your true, real-world operational costs. And finally, physics always wins. Sustained operational numbers matter infinitely more than short-burst, peak performance claims.
So are you ready to take all these efficiency metrics and calculate your actual return on investment? Because that is exactly what we are going to do in our very next lesson, calculating cost and ROI for hardware. Be sure to bring all the JTH math we learned today. I want to thank you so much for hanging out with me for this explainer. To continue your Web3 education, be sure to head over and visit us at forge.college, where you can find tons more lessons just like this one. See you next time.